think we'll go ahead and get started with today's seminar. Welcome to this research seminar, which is being hosted by the Center for Transportation Studies here at the University of Minnesota. My name is Linda Prisen, and I'm the Director of Research Administration at CTS. And we are offering a number of seminars this fall that feature research projects related to transportation. So we'll have one again next week, November 1st, and the week after that on November 8th. They're all held from 3:30 to 4:30 here in this room. And CTS will send out announcements about the topics and the speakers prior to those events. This particular seminar is being held in conjunction with the CTS Transportation Infrastructure Council, which met previous to this seminar session. A couple of just housekeeping items. Today's seminar is being streamed on CTS's website. So in addition to the audience we have here in the room, we do have a remote audience that could be watching the seminar live. And you'll notice that this microphone does not project my voice in this room, but it is helping for the remote audience to hear my voice and the presenter's voice during the seminar. We also record the seminar for later viewing after the fact. So if you know of people who might be interested in this topic but weren't able to attend the meeting here on campus or attend on the web, you can certainly pass along that information to them. And we will ask that you hold your questions until the end of the seminar, and again, use this microphone, and don't be alarmed if it's not projecting in the room, but people will be able to hear you, and we'll ask you to hold the microphone real close and ask your questions at the end of the seminar. We can take questions online as well, and there's a chat box up in the upper right-hand corner for the viewers online to type in questions at the end of the presentation. So at this point, I'd like to introduce Mike Sheehan, Olmsted County Engineer, and he will be introducing today's presenter.
Thank you, Linda. Today's presentation is going to be Culvert Pipe Materials and Durability, Making the Right Selection for Minnesota. And Professor Jeffrey Marr is Associate Director for Engineering Facilities at the St. Anthony Falls Laboratory here at the University of Minnesota. In his role as Associate Director, Jeff oversees the Applied Research Team at the St. Anthony Falls Lab, which has ongoing work in the areas of urban stormwater, hydraulic modeling, wind and water power, river engineer restoration, and technology development for field monitoring. Jeff received his BS and MS in civil engineering from the University of Minnesota in 1996 and 1998, respectively. Jeff's personal research interests include water hydraulics, river engineering and river restoration, sediment transport, dynamics, and wind engineering. Currently, Jeff is serving as Associate Director of the Connell's Wind Energy Research Consortium, a newly formed wind research center at the University of Minnesota. Jeff is also a licensed professional engineer in the state of Minnesota. So with that, I'd like to welcome Jeff.
Thank you. Thanks. Okay. Well, thanks everyone for coming today and for the people online. I'll be presenting some work that was completed recently here at the university. I want to acknowledge my collaborator, Craig Taylor, who was actually in the lead role on this project, but he's at a conference this week. Again, this project just completed recently. The funding for this project was provided by the Department of Transportation here in Minnesota. I've listed the work order number for that project. And we've also got some funding from our laboratory where I'm from, which is the St. Anthony Falls Laboratory. And then we wanted to thank the members of our technical advisory panel, and I've listed their names here. We worked very closely with our TAP group in this project just to get insight from the districts around the state, as well as the metro area group here at DOT. And then, of course, the Center for Transportation Studies, who's not only hosting this seminar, but also does a lot of facilitation for those of us that are researchers here at the University of Minnesota. So what is this project about? This project was focused on improving, really the long-term goal is really set on improving culvert design, installation and monitoring practices in the state of Minnesota. And we're expanding pipe material options for design consideration. We're evaluating current practices, and we're optimizing design for service life and performance. Now it's important to note here that this is the first step in what we hope is a number of projects. There's quite a task at hand here, and this was the first project in that series. Our project goals, I mentioned it before, really evaluating current practice and developing a research roadmap that will update design, construction, and monitoring practices for culvert installation in Minnesota. And as I said, phase one of the project, we're working on developing recommendations for improving practice and developing a set of research needs, and I'll present that in this presentation. So quickly, just a review of culverts. I think many of the people in the room are experts in culverts, but I just wanted to make sure everyone listening here is on the same page. These are engineered structures that are all over the landscape, and in Minnesota there's many, many of these culverts, and they range in size and location. They primarily are conveying water from one side of an embankment to another, and they're typically associated with our transportation infrastructure. They are also critical for safe conveyance of water through a watershed. And so this is really an intersection point of the water resources in our state and the transportation infrastructure. And it's really an amazing thing to think about what's going on here. In the state highway system, we'll talk about a database that the DOT runs. It's called HIDE Infra. That database contains over 95,000 culverts within that database, and that's just in the state, at the state level. There's a range of size and capacities. We've got highways, county roads, minimum maintenance roads, driveways. I mean, really every scale of transportation system we're dealing with culverts. Okay? And they're a major component of local and regional drainage network. So they're impacting our drainage system, our transportation system, public and private property, health, life, and safety. This is a nice image in the lower corner from Duluth, Minnesota, from this spring, where a road was taken out. And not necessarily related to the material of the pipe. I don't think it mattered if it was concrete or plastic. But it shows the importance in this intersection of our water resources and the transportation system. This next slide is taken from the database, this HIDE Infra database. And I don't know if you can see it here, but you'll see different colors on the major highway systems. And every dot on this graphic is a culvert that is in the database. And you can just see essentially the whole length of all of these major roads. There are culverts. And the fact that they have different colors means that a field person has been out and evaluated that culvert. So the person hours involved in this is substantial. And this map doesn't include culverts that are outside of the DOT's jurisdiction. So county roads and local road systems are not included in this database. So a few slides here on the design considerations. And again, this may be repeat for people, but I thought it was important to just take a step back and think about when you're tasked with designing a culvert, what are we thinking about? So obviously we're thinking first about the hydraulics of a culvert, and perhaps that might be the most important and most common thing people will think about is we're going to size our culvert to handle a certain flow, a certain return period of flow, and this is done. There's a lot of background behind that and estimating what those flows are going to be. We're not going to get into that today, but it's obviously one of the top of the list for an important design variable. We're going to try to keep within a budget, so our cost is important. And then we're going to talk about service life, the length of time that our pipe wants to be in the ground and that we're not going to have to replace it. So I talked about some of these things, the hydrologies, I mentioned already, geometry or topography of the crossing, so taking plan view, looking at what that crossing looks like, what kind of lengths we have to span, what kind of the slopes, the soil materials, and other local hydraulic issues. I didn't list here some of the soil soil materials, which are also important. All of this is somewhat laid out in what is called the drainage manual. And I've got a copy here. I love the cover of this, which actually says drainage manual. It's very clear. But this has, it really is kind of the MnDOT guidelines for how they do pipe material selection and culvert design, as well as storm sewer design in that. And it's an important document that the teams touch back on all the time. Other design considerations that people may not think about. Environmental considerations are important, and they become important when we talk about expanding the pipe materials that are traditionally looked at. So environmental conditions, I mean things like the soil resistivity or pH or other complexities with the bed material. Abrasion within a pipe. So the impact of sediments flowing through a pipe on that pipe itself. A topic that's of importance right now across the country is aquatic organism passage or fish passage. It doesn't have to be fish. It can be any kind of organism. It can actually be the passage of mammals and other turtles or other animals like that. And so considering whether our pipe is designed for hydraulic conveyance or providing a conduit for white-tailed deer to move through the watershed. This is becoming more of an important consideration in designing and sizing culverts. Life cycle cost, really understanding what is the full cost of our installation. So not only the capital expenditures at the front end, the installation costs, but operational and maintenance costs and replacement costs of that pipe are important. So again, back to this project. 3 issues really motivate the work. The actual service life of infrastructure is less than expected. And this is an observation that's been made by our colleagues at the DOT and out in the districts, and I believe is the motivation for why this was a project that was identified and listed for one that needs some research. Is that we see culverts across the state that should be lasting longer, and they're not, and it's a real problem. And we know that some of the feedback we've gotten is people go out and survey their infrastructure. They see problems coming. They see a lot of pipes that are in poor repair, and they are predicting large numbers of failures and replacements needed in the future. And why is that? So there's a near-term problem of fixing what is broken and will break more, but also thinking about what we're going to do in the future. There have been advances in pipe materials, and there's a broader range of pipe materials available to designers, and there's also a federal requirement that has come out that is challenging or asking the states to be intentional about considering alternative pipe materials when they bid projects out. And so this is something that our DOT is responding to, and so in order to make those accommodations, we want to have best information available so that they can implement it effectively. And then number 3 is really the long view. MnDOT seeks to improve and update guidelines to improve practices statewide. So that's our motivation. Our project started out with a literature review, really looking at the literature, what's been done, what's published at the federal level, and what are the states doing, different states that have looked at this problem. Here's a partial list of some of the publications that we've looked at. I'll talk about the first 2 a little bit or refer some information from the first 2. I'm not going to spend time going through all the literature, though, today. I will mention that this phase of the project is complete. There is a project report, and that is available by contacting the Center for Transportation Studies, and you can get a PDF of this work. So some of the major findings from the literature. I've provided here the list of pipe materials that we identified through our work that are kind of at the top end of consideration for our state in the northern U.S. and in Minnesota. Reinforced concrete pipe is obviously a well-used and the most used culvert type installed. Galvanized corrugated steel pipe, and then aluminized corrugated steel pipe, polymer-coated pipe, and then HDPE and PVC are also listed here. And I'll talk a little bit about each of those in a bit. One thing that this project, I'll mention it very briefly, is we spent time, in addition to doing this literature work, we spent time interviewing people in the district, so on the public side, working with the DOT. So we had an interview with at least one representative from every district. And we also talked to the private sector, people supplying these materials, and just the names of those interviewed are kept confidential, but the results are summarized in our report. And it's really interesting feedback about people's perceptions of the different materials, their strengths, their weaknesses, and where the work needs to happen to improve practice. One thing that comes out, however, is that you can do all the textbook design and so forth, but really the material can limit pretty quickly the service life of the culvert itself. So it's a very important component to be considered in design. So what causes pipes to deteriorate? This is findings from the literature as well as from these interviews I mentioned. So we can talk about the soil pH, the acidity, the alkalinity of the water in the soil, and that has an impact on the pipe itself. Soil resistivity, which is a measurement that we can make in the field that tells us about the number of ions in the solutions around the pipes, and can tell us about corrosion. Chlorides, sulfates, as well as abrasion, which I mentioned before, mechanical erosion of pipes within the pipe itself, and then a whole bunch of different loading categories, structural loading, freeze and thaw cycle, which is important in Minnesota, and then relationships of the bedding of the pipe itself on its lifespan. And then surface cracking I listed as well, which is a deterioration that is seen in some of the plastic pipes as well as in concrete, where you just see micro cracks forming, and that can lead to deterioration of the pipe. So a quick, the next few slides I'm going to show are really just summarizing the different material types that we identified, and then I'm going to give you some of the findings that we see in the literature as well as some of the feedback from the research. And I should have said at the beginning, I hope that when I get through these slides we can have some discussion. There's certain expertise in this room, and you guys would certainly be interested in feedback from the audience here and then as well as online. So RCP is the most common pipe type in the state of Minnesota. It's a very durable pipe. One of the biggest problems that we have in the state is joint separation. So adjacent segments of pipe separating, and a whole bunch of different things can happen at that point. The best performance is between pHs of 5 and 9, and within that range, service life can exceed 100 years. Salt can be an issue for reinforcing steel within RCP. So if we're having cracks that expose that steel, salt can be an issue. And we know in Minnesota we like to apply lots of salt to our roads in the winter time, and so this can be it's not very well studied. We know something about the salt concentrations in winter, but its direct impact on pipes has not been studied. And it's easy to adjust for abrasion or salt through design, so we can spec thicker concrete over the steel, reinforcing steel, and so forth. Galvanized corrugated pipe, a zinc galvanized pipe, also very common. Inexpensive, it's lightweight and easy to move around, and it's available here in the Midwest. So this is a pipe that's installed very often It's, I think, the second most installed pipe here. It has poor or weaker abrasion resistance. Now, that's a relative term. What does that mean? But it does erode by abrasion. So if you've got lots of bed load transport, that can wear down. A solution to that is lining the invert of the pipe with some concrete, so you can add a little more protection. The service life for this steel pipe, there's two methods that the DOT, our Minnesota DOT, uses to estimate the service life, the lifespan of this pipe. And they use variables of soil resistivity and pH. So if we can get those measurements out in the field, we can project and estimate what the service life will be for that material. And a ballpark design life for this material is 25 to 50 years. One of the newer metal pipes that we identified as aluminized corrugated metal pipe. I actually don't know how long aluminized pipe has been around. I would guess it's been around a long time. But it shows up in the literature that it's a newer product that's going into transportation infrastructure. And it has a lot of good things going for it. It's less commonly used in Minnesota. In our interviews, we got a lot of positive feedbacks from contractors, from the pipe manufacturers, of course, and from our DOT districts. They like this pipe. It has it's lightweight, and it has the same abrasion resistance as the zinc galvanized, but again, concrete can help us out. But here's the important piece, is that the service life, this is published results. I think there's some results in Florida that have been published, as well as in some NCHRP reports, that the service life can be almost 3 to 8 times longer than zinc galvanized. There's polymeric coated corrugated metal pipe, and I've shown an image here of this pipe material. This is less common in Minnesota. It's also lighter weight, but it's not extensively studied. There's not a lot of literature published on this, and our interviews with people, very, very few have been implemented in Minnesota. One of the downsides is that the coating that's put on this pipe is susceptible to abrasion or surface damage. So even installing the pipe, if you scratch and damage that surface, it can expose the raw metal, and then that can lead to a corrosion in a localized spot. The suppliers do provide coatings that you can go in and repair those damages, and so there is methods to control those problems. But really, the point here, I think, is that this is an interesting pipe. There's not a lot of information on it at this time. But the service life, the upshot of this is the service life is really good. It's a 100-year service life, so it's corrosion resistant if you can keep the coating intact. Plastic pipes is another subset. So HDPE and PVC pipes are found in the literature and used. Minnesota has several installations of HDPE. It's lightweight. One of the problems, especially with PVC, is its performance in really cold extremes, which we have here. PVC can become very brittle and break. Now, and one of the things that we heard from our interviews is that the installation is very, very critical to this. So the bedding you use, the compaction, and so forth is really important in installing these pipes. But the pipe, its benefits are as good against abrasion and scour and solutes. Service life is very high as well. And so we found in some of our surveys that the people like this pipe. It's got a lot going for it. The challenges are really on the installation, and that's where you'll see in our recommendations. That's where the work has to happen. I mentioned before that we spent time after we kind of got through our literature of talking with district representatives and also suppliers. And you can see the report for a summary of some of the comments made. Okay. I'm going to switch gears a little bit and talk about databases. when this project was initially scoped, we had hypotheses for how we would approach the problem. We know that in this state, a lot of our state agencies have a pretty tremendous georeference database about water quality or soils, and we had some questions about that I listed here. You know, can existing spatial data sets help inform the performance we're seeing in the field? And then what are those data sets and how detailed are the data? And so one of our tasks was to really dig into these databases for the DOT and help identify them. So I'm going to list here a few of the databases that we looked at. There's an NRCS web soil survey, WSS data that we looked at and is actually very interesting and useful. District 3 here in Minnesota actually developed a pH map that is interesting. And then there's the MnDOT has, I mentioned this large database, 95,000 different culverts called HIDE Infra, and I'll talk about that a little bit. We also looked at databases from the USGS, just the surface water database that they have, where they have pH at some state gauging stations in the state. That turned out to not be very useful. The MPCA has some shallow groundwater information. Again, we concluded that the information there was too sparse and not useful for the DOT. And there were a number of, probably 2 or 3 other databases that I don't list here that we had hopes that there was some information there that we could tie into and kind of bring databases together and kind of see, in particular, this HIDE Infra database where we've got lots of information about how culverts are doing. Can we lay over that some information about pH across the state and try to draw some correlations? I remember at the very beginning of the project, we wondered if our karst region of the state in the southeast, if we would see some trends for how different pipes do in that part of the state versus on the North Shore where we have a lot of bedrock. But again, it didn't pan out in that way, but that's still useful because we provided some information to DOT on where there was good information. So I'll start a little bit with the WSS survey. There was 216 entries in this fairly small database. There was 53 locations where there's pH and soil resistivity. And therefore, these are sites that we can actually use the methods for, you'll remember for steel pipe, I mentioned there's a couple methods for estimating service life of these pipes. And so in these locations, we can go through that exercise. At the same time, District 3, which is in the north central part of our state, had some pH information and pH maps. And so, again, you can do the same thing for your steel pipe. And what you'll see in this figure here is I'm plotting both the NRCS data against the District 3 maps. If they're perfectly correlated, you'll see a one-to-one line. What this is showing is that's not the case. It's not too bad. The NRCS is it's reporting lower values of pH than the District 3 map. But the take-home for you all is that for steel pipe design, this is important information. This is a tool that designers can use. If we can get pH and soil resistivity maps, now they have a tool. They can go in these Caltrans equations, and they can actually give an estimate for what service life is going to be. And this is a take-home for this project. This is the kind of information we want to enhance in the next project, and is one of the things that we propose we should do as a next step is to further the maps. Do what District 3 did across the state. Fill out the WSS data, which I showed in the previous slide, the red dots here. Can we add more dots to this map and to help out our designers? The HIDE Infra database is a DOT database. I'm not exactly sure. Maybe somebody in the room knows when this database was started, but I don't know the answer to that. But it was a database set up for field people to put in what they observe in the field about the status of culverts. It's constrained. It doesn't look at anything over 10 foot in span. It also includes structures and other special structures, manholes, catch basins, and so forth, and there's other information in there. We were focused mainly on the culverts. The rating system is kept very simple. 0 to 4. 0 means you don't have any, you can't rate it, you can't get to it. 1 is excellent, and 4 is very poor. 3 is poor. And so 3 and 4 are pipes that now you got to start thinking about fixing them and repairing them, replacing. And so I showed the map earlier in the presentation with the colored dots. Each of the colored dots represents 1 through 4 on this scale. And so all of the culverts, those 95,000 culverts, are in there. And there's other information about those culverts, some of the geometry information, whatever they can gather on the type of problems they see at the site. So we spent actually quite a bit of time with this database trying to draw out some information about current practices, current infrastructure that's out there. What can we see? What are some trends and correlations we can see? I'm going to skip this for time. This slide I'm just talking about what are our goals for using this database. So here's a slide on some findings. This is usage of pipe material across the state. It's broken down by district, so each column is a district. The metro is the Twin Cities metro area, and then statewide is just an average of all of these, all of this information. And what you can see is concrete is very prevalent. It's about 76% of all the culverts out in the field. As steel comes in second, and then plastic is a small subset, and plastic is really limited to HDPE. We were surprised at how much concrete is out there. I don't know if that squares with the expertise in the room, but the next slide here is average pipe condition by district. So here we're looking at those 1 through 4 ratings that I listed before for high infra. That's the y-axis on the left of the plot. And then the x-axis is the district. Metro is the Twin Cities, statewide. And you see the 3 different pipe types here. Now you don't see any 4s on this. Now remember, this is averages, so you're not going to see your outliers, which are your 4s and some of your 3s. So it would be interesting to actually break this out by district and look at the distribution of all of the pipes in a district and see how we're doing, how many are in the category 3, category 4. But what you can see here is that in District 1, for example, which is the North Shore, Duluth area, and the Arrowhead region of the state, we have some of the steel pipes have pretty high average poor condition. Region 6, some of the concrete pipe is getting up into the 2s and so forth. So we can come back to this if people have specific questions on, because I can imagine people work in specific areas of the state. And then this is some other, this table is interesting as well. So here we're talking about road damage. So we have culverts that are passing under a roadway. If the culvert is deteriorated to a certain level, we're going to see impacts on the road surface above. In hide infra, you can the person entering the data can flag certain things that they observe and for road damage. So a void in the road, for example, or a depression or a swale of some kind of road distress. Our survey of the hide infra showed that the concrete pipe is correlated with the most road damage out there. One question we asked, and we talked with our TAP at length about this, is this real or is this perception? Because with something that has road damage, it's really easy to see it. But you might have, for example, a metal pipe that's also in poor repair, but because you don't see it on the road surface, you really don't appreciate the extent of the damage. So it could be that this road damage just presents itself so clearly. But we do know that joint separation is a major issue, and I don't spend a lot of time in this presentation, but in our group, a lot of time was spent talking about joint separation with concrete pipe. It is one of the big issues that the DOT is well aware of. It came out in this project. We talked a lot about how do we solve joint separation problems. This table, which is data drawn from summary of the height infra data. So 18% of the reinforced concrete pipe have joint separation issues. So you can see if you look at the far left column is our districts, and then the second column is the percent concrete pipe with joint separation of all of the pipe in the district. And you can see the mean is about 17.5%. You can see it spiking in District 4, in District 8, almost 40%. The next columns to the right of that break that down. You can see columns for distress only, void only, both, or all damage. And we compute in the far right column the percent of road damage of the pipes that have damage. How much of that is coming up with road damage? And you can see that mean is 14%. So for joint separated pipes, 14% result in road damage according to the height infra database. So that's a substantial amount that's impacting actually the driving surface and is a point where you would need to intervene in the failure. Some other findings, I mentioned that, well, this is a different 14%. 14% of poor and very poor rated pipes have associated road damage. And then I didn't show this, but the medium pipe sizes, 24 to 36 inches, are most susceptible to joint separation. Another observation. Okay, the next phase of our project was to develop some recommendations. Again, this was done with our TAP member input, and so I'm just going to show a few of those slides. We ended up with 12 recommendations that show up in our final report. I'm not going to go through all 12 today, but some of the ones that I think are the most important is a recommendation first here for service life, that really the designers should establish goals for design life, for service life for these culverts, because that really sets the direction for your material selection process. So what is proposed here is a 100-year design service life for centerline and mainline trunk highway culverts, 50 to 75-year design service life for entrance culverts. And these two bottom bullets really talk about this was drawn out of the interview processes we did, and then a report, Perrin and Javieri, an interesting economic analysis that showed that you might spend more for your capital expenditures on the front end, but the costs of going in when you've got a failure at the road surface and intervening in an emergency situation far exceeds the front end costs, which makes sense, but hard to sell when you have a fixed budget, right? So you set those goals up front, 100 year and 50 and 75 years. Again, we spent a lot of time talking about joint separation. The conversation comes back to gasketed and gasket joints, and our recommendation is that gasket joints should become the default for concrete pipe of all sizes. And I think all pipes are tied now, but this was and this is an area that more work needs to happen. It's easy to say that, but then how do you implement this kind of a recommendation? Our third recommendation here is consider adding a third party or contractor for nuclear density testing or dynamic cone penetrometer testing for culverts 18 inches or larger. And this is really, again, drawn out of the interviews that compaction is a major cause of joint separation and deflection. And so we could talk about this after, but this was really one of the major, most lively parts of our project in talking about this issue. You can imagine as you go from the districts Or you go start in the metro area, you go out to the districts where they're putting projects in the ground, and then you're going with the manufacturers themselves. There's a lot of different viewpoints about compaction, how you should monitor it in the field during construction and so forth. So that's that recommendation. Our work showed that aluminized corrugated pipe was well liked by people kind of across the board, and that so we're recommending that the 16 gauge aluminized corrugated metal pipe should become better incorporated into practice. So you can play around with the language there. Should you say it should become the default metal pipe or better incorporated, or that's for the DOT to figure out how strongly they want to word that. But again, our feedback is it seems to have a lot going for it, and with especially focused on the better service life. Concern for another recommendation focused on HDPE. Our surveys showed that lots of people like this pipe. It offers a lot of flexibility and cost savings. It has a really good service life, but there's concerns about installation. And so we're recommending that there's inspection methods developed that help this material pipe become more implemented in the field and incorporated into projects. Another recommendation has to do with abrasion. I'm going to move forward. This is really just saying we should adopt existing abrasion methodologies that Caltrans has adopted. It's not perfect for Minnesota, but it works, and it's something that we can just adopt here in Minnesota, or at least take what applies here. Another recommendation that's on post-project evaluation, kind of monitoring inspection through video. I'm going to keep moving, though. And then finally, the last few slides are on our roadmap that I've talked about. So again, working with our TAP, we developed 4 research needs. They're listed in this slide. Number 1 is, I mentioned, an HDPE inspection and testing methods. So spending some time really on that problem, developing an understanding for what the challenges are for that pipe material and putting it in different applications, and then coming up with ways that can cost-effective ways of inspecting the installation. The second project is on joint separation. Again, I mentioned the lively discussions we had in that, and really it's a problem, an area that requires more work, another TAP that's focused just on that issue, and the suppliers as well involved in that. The third is a process-based abrasion model. That one touches some of the work we do at St. Anthony Falls, where we like sediment transport a lot. So we think that there's things we can do taking from the field of hydraulics and sediment transport and knowing how the shear stresses of moving gravel can wear on pipe of different materials. And then finally, the steel pipe service life map. And I mentioned District 3 and how there's some pH information, some resistivity that's helpful. We feel that that's maybe the first step. And so that's a project that I believe that the DOT went forward and is trying to get in the ground or get implemented. The goal is to develop a statewide steel pipe service life map based on a Caltrans, what we call the California method to improve steel pipe design. And so that's really about going out in the field, taking lots of measurements, pH and soil resistivity, georeferencing that data, and developing these maps. And so we'll see if that work goes forward, and it will add some capabilities for steel pipe design for the state. So that's it. Here I summarize conclusions. I'll just read them quick. Again, the project was motivated by MnDOT really looking forward and wanting to update their methods of design, bring in more pipe material selections, and then really address a service life issue. We kind of validated that high infrared has some very valuable information in it, and that was a question that DOT asked us to look at. We looked at some new pipe materials, HDPE, as well as aluminized corrugated metal pipe. We talked about RCP and some of the issues. It's a durable pipe. It's a strong pipe. It's got problems with its joints, and so there's more work in this area needed. We talked about installation monitoring is key for some of the plastic pipes, and then I suggested some of the road maps. And I think I'll just end there, and we can move into some discussion and questions. Thank you.
Great. Thanks, Jeff. We'll open it up for Q&A now. Does anybody in the audience have a question for Jeff?
Regarding the service life for steel pipe, you correlated that with the map of pH, but have you considered the design provisions, particularly it's shown a poor service life because then that has no corrosion provision, structural design provision for corrosion for steel pipe?
Yeah, so we didn't get into that level of detail at this stage. We're really looking at trying to draw out from Hyde Infra what we can about the steel pipe in the ground. Your question is about the method for estimating.
There are no corrosion protection structural design provisions in the current that designed for steel metal pipes at this point, but in the future we are likely to incorporate more corrosion requirement, and basically the current pipes are not designed for corrosion, so it shows poor performance at this point.
Okay, so for example, a zinc galvanized pipe is protected for corrosion, but you're saying that in terms of the structural capabilities, the structural strength of that pipe,
you could increase the thickness of the pipe and
Yeah.
get better life.
Yeah.
For example, you show service life 25 to 50 years, but if it was designed for corrosion for 100 years, you could probably design for 100 years life of a steel pipe.
Yes. We did not look at that, but I think that in the exercise of, because as you know, there's different gauges of steel pipe as well. There's a couple variables there that we didn't look at, and I think it wasn't in this scope, but I'm sure with the efforts to update the drainage manual, that the point you're bringing up will surface at least.
Thank you. Other questions?
I noticed in the when you looked at the pipes for like Metro, you showed 8% separation in Metro. Some of the other districts had like 39%.
Mm-hmm.
Did you have any correlation? Was it because we use more granular material and the bedding is better in Metro, or did you guys look at bedding?
That is I'm not sure how much I'm going to try to find that table. How much time we didn't, I can't give you an answer for why we see the ranges there and try to attribute it for what's on the ground and regional variability. We could maybe talk about it, but
I was surprised to see too that concrete pipe, that steel pipe was doing better than concrete. So the rating must be more of a kind of a flow line thing, because I would imagine the concrete pipe is still intact, but
yeah.
If it's got a 100-year life, it should be,
Yeah.
So.
And that's the point I made about the concrete pipe is not, the invert's not rotting away, and this, you might have some where the steel's exposed, but not like you'd see with a steel invert that's just gone. This is, you have joint separations, and you've got you've got piping, or you've got sediment coming into the pipe, and it's really obvious, right? And so it could be skewed. The fact that, I think your point of what are the inspectors seeing, and are we able to actually separate that in the database? So I think the point is perhaps that we have to be careful with saying that concrete's failing more than steel, right?
So my question relates to Tom's also, is that when the pipes are installed, culverts are installed, what was the level of inspection? Not just what was the material type, but this whole question about what happened during construction.
Yeah.
If you actually plotted the inspector time in those districts during construction, would it correlate to good and bad outcomes?
Well, so that's part of the lively discussion that was had, and you'll remember, I think it was, some of these mid-sized pipes were having more trouble, and the thought that the group had was that those pipes are there's so many that go in that you can't inspect those. You just don't have somebody on site every time. But the larger projects, you tend to have somebody there if it's a bigger project, bigger money. But exactly what you're saying is the issue of inspections. How can you? Everyone seemed to agree that that's really important, to have inspectors in to make sure there's consistent methodology, that you're making good measurements of compaction. But how do we do that with limited resources? And I don't know if I answered your question. We did not get into that information isn't in the database. Like, you don't have number of hours inspectors were on site.
And so I guess, again, sort of the economic impact of some of these decisions that get made. Earlier in the day we talked about, again, this economic piece of this, and that it seems like some future work here would be related to that, because, well, that's just my suggestion, I guess.
Yeah.
That we have these failures that are clearly costing us a lot of money. What is if we would have spent a few more hours inspecting, we would be saving hundreds or millions of dollars, it would seem like.
Yeah, we would agree.
Well, I would agree that inspection is really important, and a lot of times you'll see in local roads the backhoe out there holding the pipe down and throwing the dirt around, and you're not getting good compaction along the edges of the pipe when you're doing that. But I think one of the things that you talk about really strongly is the separation, and there is a lot of separation on the old pipes because they didn't tie them in the old days. But I think modern day procedures now are requiring the pipes to be tied. And when you get the gasketed pipes, you got that gasket lip on there. That makes that a little harder to get those tied in some cases. So it might be something that you're getting a skew because you're looking at data on old roads with old pipes, and it's not the current situation and problem.
Yes.
So just take a look at that and look at the newer installations, because I think we've had just terrific success with the ties.
Yeah.
I
think we would agree. There were cases I didn't mention, but we did have a field visit. I didn't go on it. My colleague was there in District 6, and they toured some. There's some really old installations, but there was some. I think there was one that was just 12 years old that had some separation problems. So I'm not disagreeing. But like everything, there's exceptions where and so it's important to ask why. What didn't happen there? Is it an inspection issue, construction issue? Yeah.
I think the ties, they are not designed structurally to keep the joints closed, but they help in keeping the alignment better at the time of construction. And I will be curious to know how much of those joint separation happened during the installation process versus later.
Mm-hmm. Yeah, and I don't think that, of course, our study didn't get into that, but it has been talked about that you would do a 30-day inspection. I know specifically for some of the plastic pipes that you would do an immediate mandrel test where you're pulling a mandrel through the pipe, but you would come back within 2, 3, 4 weeks after a project is opened to re-inspect. I think there were some results that said, that some hypotheses that a lot of this stuff does happen right after construction or right during. It's part of installation that something gets knocked loose when they're finishing construction or something like that.
Other questions? I did have one. So I'm wondering, with the District 3 pH map that you showed, how much in your future research, because that does sound exciting, how much will that vary across the state, sort of in your estimation, those pH values? And then how is that determined now without those maps? Is it a field test during design, or how does it work currently without knowing that data?
I'm not. I think it's probably case by case. I think that because my sense is that that design life isn't the first variable that they're using to pick the pipe, and perhaps somebody can expand on it. But I don't think. I think it doesn't start with trying to say what the service life is. So if you don't have pH and resistivity, you figure out something else to do. The question of how it varies across the state is going to be really interesting. I mean, what scale is the variability? I mean, if you're down in wetland, lowland, it seems to me like it would vary even within a watershed of smaller watershed that you could find pretty dramatic variation. And then there's also the annual cycle in pH that most certainly is there. And so, how do you then take that variability, regional, kind of spatial and temporal variability, and get a number that actually can work for design? I think that will be interesting to figure out.
All right. Well, please join me in thanking Jeff for his presentation today.
Thank you. Thank you.
And I'll just close by indicating that there is a form that will document PDH, or Professional Development Hour Earned. If you're interested, and that form is in your packet. It's a white sheet in the very back. The next seminar, as a part of the CTS seminar series, is next Thursday, November 1st at 3:30 here in this room. And Ensar Bekish, he's a research associate in the Human First program here at the U of M, will be making a presentation on driver task analysis, pedestrian collisions, and possible solution for left-turning buses. So we hope to see you at that presentation or a future seminar here at CTS. For parking validation, if you were here for the council meeting, you can see Joe after we're done here. And thanks again for coming. We hope to see you at a seminar again soon. Thanks.